Okay, so here's just, again, here's an example, here's an experimental result. This is the Hersenite cycle. This is the conventional ferrite that people have been developing. Zirconia is essentially inert. Alumina takes part in the reaction. And notice that if I heat up both of these systems to 12 and 1300 C, the conventional material, I make no hydrogen. I need to reduce to a higher temperature. However, with the Hersenite system, I make substantial amounts of hydrogen. And in fact, if I reduce to 1400 C, I'm making twice as much hydrogen. It is not until I reduce at 1500 C that the conventional process is better. However, if I go to 1525 C, that turns to a liquid and it's all over. I can never get the ferrite back. So the window of operation is very small. You got to achieve very high temperatures. Whereas with this other process, I have a very large window, hundreds of degrees. And in fact, what I'm showing you is that we've reduced the upper temperature of reduction to split water by about 250 degrees Celsius. And that is pretty significant. Also, because of the thin films, these reaction rates are very fast. So here I'm showing you a thin film versus a conventional bulk material ferrite. Notice at this rate here, I have a number like 40, here's 0.4. I'm looking at reaction rates that are about 100 times faster using the thin films. So again, as I mentioned, thin films are driving the cost of PV down. Thin films also really, they happen to be the link that is going to also drive down solar thermal. And in fact, I can achieve about 50% of this conversion in about 20 seconds. Now, what about cost on this? We're looking at two systems. We're looking at a large central receiver, which is this, and these numbers come from the Department of Energy H2A program. These numbers were reviewed by a company called TIAX that basically compares technologies and sort of makes sure that you're consistent and apples are being compared to apples. So these are TIAX reviewed numbers. And what's important here is that the 2015 target is $6 per kilogram of hydrogen through solar thermal. The 2025 target is $3 per kilogram of hydrogen. It looks like this line was shifted a little bit when we switched, but it should be up. And the point that I want to make is that using the base case economics for the Department of Energy, this process is able to potentially hit those cost targets. But what's required is that I have to be able to carry out that reduction oxidation reaction in about 12 minutes per cycle by 2015 and about 2 minutes per cycle by 2020 in order to hit those targets. But it looks like it's doable if we can keep these thin films hanging together. Now, here's what the triple play looks like in practice, okay? So here you have the solar field, the heliostat field. You have your receiver, and I'm making 100,000 kilograms of hydrogen a day. It requires 900,000 kilograms of water to be fed. I'm also producing 800,000 kilograms of pure oxygen, and maybe there's some value for that. I'm going to bring in seawater, and I have a heat exchanger here. And what I'm going to do is I'm going to take that. I have a recirculating distilled water system. I'm going to take that water and make steam using essentially waste heat. In other words, inside that solar reactor, I can very efficiently transfer heat. But I've got to take the hydrogen and oxygen coming off at 1,000 degrees back down to room temperature. I'm going to use that sensible heat to basically drive the first effect of a multiple effect evaporator. This technology it exists today. It's used in the food industry quite extensively. And what happens here is that with 0.35 kilograms of steam that I'm recirculating, I can actually get about a kilogram of evaporated water out of this. So it's possible in a multiple effect evaporator to take seawater and to not only produce the distilled water that I need to make hydrogen, but in addition to that, to supply potable water that can be used for agriculture and for drinking. So now you have the opportunity, as what I said, to be able to pull off this triple play. This is what a large-scale design may look like to make 100,000 kilograms of hydrogen a day. About 1,200 acres of land in the Mojave Desert, 4,000 suns. The annual efficiency of solar to the reactor is about 40%. The overall efficiency, including the process, is around 20 to 22%. You're looking at tall towers and about 200 megawatt thermal delivered to each solar reactor. This is a schematic. Okay, this is a real process. Now, the focus of this process is to use concentrated sunlight to gasify biomass. I don't have time to go into the advantages of that, but there are huge numbers of advantages to use sunlight to drive the endothermic reaction of steam with biomass to make synthesis gas. Once you get the synthesis gas, you can make green diesel or gasoline. This is located in Broomfield, Colorado. It's a 1 megawatt thermal facility. This is about 3.5 acres of land. Here you can see the mirrors. Here's a truck guy standing here in his tower, and this is that particular facility operating. And I want to acknowledge the support that we've got from some of the government agencies, but the point I want to make here is that these young people, this is the future. What happens in greenhouse gas reduction and sustainable energy, right? These people have a vested interest in making sure that this works. And I've been blessed to have a fantastic group of students working on this project. And in fact, I'm overwhelmed by the number of students that are interested in this. I have to keep them away because I don't have enough time. But I have absolutely outstanding students, and I can stand up here and give you this nice talk, have you think out of the box, but these are the people who are actually doing the work. Thanks.